All right, welcome back, everybody. Um, Strength of materials. I just wanted to go through a full problem start to finish since yesterday's recording failed. I don't really know how that happened, but it did. So this will be a lot like your homework, but it's not your homework. So you'll have to do that separately. And I think the quiz is a lot like this, but I'm going to kind of work it start to finish. Kind of like a full problem you would have if you go out into industry. So here we go. Fast forward, I guess, whenever you need to. Why didn't that go big? Let's see if I can make it big. There we go. All right. So here's the, that's a problem. It's inverted. So I'm going to have to stop the share. Let me pause. All right, we got it now. Let's go for it. Just thinking I could maximize this somehow, but that's all right. It's pretty maximized. This is our beam right here, 10-foot beam, 4 foot to 400 pounds, and then a 30-pound distribution. This is the cross section. And I made it wood just to keep it simple. So, and the idea here is we're given everything. This is an analysis problem. Okay. We're given the beam, we're given the loading condition, and we just want to know, is the bending stress okay? MC over I. Is the shear stress okay? And that's going to be the new VQ over IB. And I'm going to work all the way through it. So you can follow along as you need. The first step is to find our reactions. I'm not going to write this out. I'm just going to do it. So hopefully I don't make a mistake, but if I do, you'll find it, I'm sure. I'm going to do moments about this side. I'll call this AY and this BY. So doing moments about here, we're going to have 400 times 4 feet. And that is a negative, right? And then we're going to have this one, 30 times 10 times half, which is 5. And that one also is going to be a negative. So there's my two negative moments. I'm going to add them together. And then I have BY fighting it all. So that's BY times 10. That moves to the other side. So I basically divide by 10. So BY 310. I have 700 coming down. So that leaves me 390 for AY. So hopefully I did all of that right. Seems right, right? Where the larger load is over here closer to the 400. All right. So then, of course, we go for a shear and moment diagram because we need V and we need M. We need both those values and we need the maximums. So here is a V equals 0 line. I'm going to show you something kind of interesting too. 300 up, 390. Right? And then it comes down 30 every foot. So 30 times 4 is 120. So it comes down a little to the 400 here. So what is that? I'm just going to make sure that I don't make any mistakes. Looks like 270. And then it goes down 400. That's 130. So I'll make that a little shorter. And then it continues down, and hopefully From the 130, we come down another, what, this is 6 up here, 6 feet. So 6 times 30, 180. So it comes down to 310. Which is good because then it returns back up. Okay. All right. So that's our shear diagram. And what's interesting is sometimes you'll see the moment diagram, just checking to make sure my pen works, it does. The moment diagram superimposed on the shear diagram. So that just saves space, some space on the paper. So we see plus here and minus down here. So it's going to go up, kind of steep. Right here, it's going to flatten out. So up, flatten out, and then it goes a little bit negative, right? All the way over to the other end. So, and since there's a kind of a spike in there right here, it's not a smooth transition. It's got a little pointy thing in there. So that's superimposing the moment diagram onto the shear diagram, giving you M max. So we can get that from this area. So it's going to be the rectangle, the 270. This is 4 feet. So 270 times 4. I'm going to put it down a little lower. So that's the rectangle right here. That's this rectangle with a height of 270 and a base of 4 feet. And then we have to add to it this triangle, right? That triangle has a base of 4, so it's 1/2 the base. And then I need this little height right here. So it's 270 away from 390. $120. So that's your max moment. Let's see what we get here. 120 4 times 0.5 times. So there's that and 270 and our 4 times plus 1320 foot pounds is my max moment. I'm just going to calculate that again. Yep. All right, we're good. So we have V max equal 390 and M max equal 1320 foot-pounds. Okay. All right. I don't know if I can get rid of this like stuff right here. Nope, can't. So we'll just try to be more careful that it doesn't get in the way. All right. Once you have that, then you're ready to go for the equations. The problem is we have an irregular shape and we don't know what I is, right? And we don't know what C is. So I shows up here. C shows up here. B is the base. We'll talk about that when we get to shear stress. But we need I of this thing. So that means we need Y bar. So this could be a good refresher for you on finding Y bar. Remember that what we're looking for is this location of the neutral axis, Y bar. Once we get that, then we have to do the inertia, right? And we have to figure it out about that neutral axis. So that will be also some memory recall that we need to go through. Okay, remember Y bar is equal to this summation of A Ys over A. So these small AYs over A. Remember, you're going to have to break it into shapes. So I'll call this shape 1 and this shape 2. So then we need area of 1 and area of 2 y distance of 1 and y distance of 2. And we put it in the equation. Summation of, don't like my summation thing very well, ay over a. So y bar is going to equal, and I'll probably just list it. So I'll do the first one, area 1, 2 times 4. Wow, shooting lead. So that's A1 times Y1, and that's the Y distance up to the geometric center of this shape. So it's going to be 2 up, and then another 2, it's going to be 4. So that's A1, Y1. Plus, we need the A2 and Y2. So I'm just going to kind of list it out here. A is 6 times 2, 6 times 2, and then the Y distance is 1. And all of that is over the total area. 2 times 4 is 8, 6 times 2 is 12, so it's going to be 8 plus 12. So y bar equals, and this is the location of the neutral axis. Let's see if I can run this. 2 enter 4 times 8. Whoops. So yeah, that's 8 times 4. That should be 32. This is 6 times 2 is 12. So I got to add 12 to it. So I end up with 44 on top and then 20 divide. Looks like 2.2 inches. So that's the location of y bar, 2.2. Okay, and that's to here. Now, to get inertia, we need inertia about this location, right? So if you remember the inertia equation, that is like we need I of 1 and we need I of 2, and then we have to transfer it using the I sub O equals I of the individual plus AD squared, the transfer distance. So this will be good memory recall for you. Sorry, I'm drinking a little coffee. I1, that's this shape right here. Remember, base height cubed over 12 for a rectangle. The base is 2. The height is 4 over 12. So that's 1. And then 2 would be base is 6. Height is 2 over 12. So we'll run those real quick. Uh, 10.66 for I1 and 4 for the bottom one. And remember, these are inches to the 4th, both of them. Okay, so that's the individual inertias. That's this inertia about its centroid, which is right here. This inertia about its centroid, which is right here. This is D1. This is D2. So when we go to transfer, that transfer distance is from centroid to neutral axis centroid, or that combined XX axis that we had located with y bar. Okay, so try to be super careful here. I'll transfer the first one. So this is number 1 being transferred. That's the 10.66 plus, and the area of 1 is 8 inches squared. And then the transfer distance of 1 is right here. So The way I do it is I think about how far up it is to its centroid, which is 2 and 2. So it's 4 up to here. And then this is 2.2. So it's the difference between 4 and 2.2. 1.8. And don't forget to square it. So that's a step that's often missed, or this cubing is often missed. So let's get that number. So I have the 10 point, yeah, I have a few numbers in here already that I can use. So I'll square the 1.8 and then 8 times, and then I will add those together. It looks like 36.587. And that is the inertia of number 1 transferred. Now I'll transfer the second one, the 4, plus its area of the second one, that's 12. And then the transfer distance of the second one is right here. So it's the 2.2 minus, how far is it? It's 1 down. So yeah, you got to be careful here. It's 2.2 minus this distance right there, which is 1. So the transfer distance on this one looks to be 1.2, right? The 2.2 minus this 1. That's from axis to axis. So 1.2 squared. All right, so let's get that one. 21.28. Now, both those inertias are at the neutral axis. I can add them together. $57,867. All right. Take a breath here, some coffee. I'm trying to make this fit all on one page, which is not advisable when you do this whole problem, but that's what I'm trying to do so I can kind of just flip back and forth between the diagram and the equations and work through this. I probably will have to use a different piece of paper for a VQ over IB, but we can get through MC over I now. Remember that C has 2 distances when you have a non-symmetrical shape. So you have an upper C, and in this case, that upper C, here's the deflection, is in compression, and the lower C is in tension. So bending stress can be in compression or tension based on the C value you use. I think that's part of your homework, was to find both, right? Because this C is different. It's 2.2 down here, but up here, it's, what's the total height? The total height is 6. So 3.8 up above. If you just want maximum bending stress, then you use the largest C value. We'll use the 3.8. But if you wanted compression bending stress, use the 3.8. If you want tensile bending stress, use the 2.2. All right, we're just going to go for maxes. So we need MC over I. M is, we figured that out, 1320. And that's foot-pounds. And we're going to use the largest C value, 3.8. And that's inches over I, right? MC over I. I, 57.867 inches to the 4th. This foot is a problem, so we need a factor of 12 inches per foot to get rid of that. So now we have PSI. Okay, so bending stress is going to be 1320, 3.8 times 12 times, and 57.867 divide. 1040.18. Now I just made this problem up, and I actually came pretty close to acceptable bending stress. Doug fir is 900, so we're close for this to work. Maybe I choose a harder wood that's like, bending stress of 1020 and it works, kind of thing. So we're going to say it works. If your bending stress is good, then you would check your shear stress. All right, so let me show you how that works. And what I'm going to do is I'm going to peel this off and just use my diagram so I don't have to redraw that like this. And I'm going to have some more paper to work with. So when you go for shear stress, come on, focus. There we go. When you go for shear stress, it's this VQ over IB, right? So let's just talk about each one individually. We'll do the simple ones. V is from the diagrams. So V from the diagram gave us 390. We know we calculated that at 57,867. Okay. B is the width of the base at the neutral axis, because shear is maximized here at the neutral axis. Bending stress is maximized here at the outermost fibers, either there or there. But shear stress is maximized at the neutral axis. So we need the base at the neutral axis. That's 2. So B equals 2. Okay. Now, Q is the tough one. Q is called a area moment. Now, we're used to moments being forces. We've done a lot of force moments, but Q is what we call an area moment. And you can use the area above the neutral axis or the area below the neutral axis. Now, the area below the neutral axis is more complicated. The area above the neutral axis is pretty simple. It's a rectangle. So an area moment is equal to area times lever arm. That's an area moment. So if I look above the neutral axis, I have 3.8 height and 2, right? So that's my area. So Q is 3.8, that's the height, times the width, 2. That's the area right there. So area moment is area times, now I need the lever arm for this area, or the distance to the geometric center. Since this is a rectangle, that's really easy to do. It's 3.8 divided by 2. It is from, the lever arm is from the neutral axis to the centroid of the shape above the neutral axis, right? So it's this area times its lever arm, which is going to be half of the 3.8. So I'm going to write it as 3.8 divided by 2. That is your area moment. All right, so let's see what that is. 3.8, enter, 2 times. 1444. Now, area is inches squared and lever arm is inches. So this is inches to the third, right? Base is inches, V is pounds, and I is inches to the fourth. So when we put it all together, VQ over IB, we're going to get 390 pounds, Q, 14.44 inches to the third, I, 57.867 inches to the fourth, and B, 2 inches. Now let's look at the units. We have inches to the fifth below, inches to the third above. We're going to end up with pounds per square inch or PSI. Perfect. It looks like we are at 48.66 PSI. Typically, your bending stress, 1040, that's right at the limit. Shear stress, much less. Very common. Shear is normally not our control stress. That's why we always think about bending stress first, and then check in the shear stress, right? And clearly this is good. You can look up the properties of shear of Doug Furr and you'll see that it's a lot higher than 48.66 PSI. So there we go. That is a problem kind of start to finish of a simple beam, not a crazy, not a crazy loading condition, but going through it all. Having a shape that we have to find the Y bar, and then we had to find the combined inertia. And then we did the bending stress, and then we did the shear stress. So that's it. That's our goal. And the last thing in the class that we have to do is deflection, and we will do that next week. All right. Nice job, everybody. Hope that helps.